Alright, so let's go with it. We're in chapter 1, equations and inequalities. And we'll start off slow. We'll look at equations with one variable. This is what we're going to do here. And I know you know this here, so we're going to jump into examples, and we're just sort of going to go with some examples here. Also, we're going to take a look at, oh, we'll see if we do. Okay, let's go for it here. Let you guys try these here. Again, quick review. Starts off slow, gets a little more complicated. Class, I'm so sorry. I skipped one slide, and that's the problem. Sorry, as I'm looking at your the directions. I should probably put directions, huh? The directions for this is not solve the problem. The directions for this is find the domain of the variable x to the following equations here. Sorry, let me go back. Sorry, my fault, totally. We talk about domain. Domain is all the stuff that whatever you can plug in so that it's not undefined, right? So, sorry, going a little ahead of myself here. So not solving the problem per se, but just looking at domain. So for number 1, looking at this here, the only problem we have with, two problems we have with domain. One is fractions, and the other is square roots. And remember with fractions, what can you not have on the bottom of the fraction? 0. What can you not have inside a square root if you're dealing with real numbers? Negatives. So in this case, we do have a fraction, but the x is actually on top, so that's not a problem. The problem is that the bottom not be a 0. So in this case, everybody okay with a negative infinity to positive infinity as your domain? I actually should have put directions here. That'd be good. For number 2, look at this one here. Now we got ourselves a problem, because in our denominator there's a possibility of it being a 0. So what does x have to be, and if there's going to be a 0 on the bottom? Absolutely, it'd be 2, right? That's pretty easy to have. How do we do it algebraically? All we do is we set the denominator equal to 0 and solve. In this case, move the x over, but that's our problem, right? That's what x cannot be. So interval notation, can you write for me the domain for b? And it should look something like this. Right, you go from negative infinity to 2, and you got a parenthesis there, means you're not including that 2. Then you put this little u called union, which means right at 2 there's a break. Then you go off from above 2 to infinity. Okay, good there. And the other problem is the square root problem here, C. All right, in this case, look at this one here. We've got a square root, and we talked about it here. Square root cannot be a negative. Could be 0. So we say the domain of the square root of any number is the non-negative real numbers here. So all we had to do is just do this. Solve this algebraic equation. So x minus 1 has to be greater than or equal to 0. Adding that up, and I think we're okay there. Is that good? And then can you turn it into an interval notation? Alright, hopefully we did it here. Again, it's x greater than or equal to 1, so we have a bracket. And again, bracket means we're including that number. And then we're going off to infinity. Kind of funny infinity symbol, but it should be infinity. Okay, and then sometimes the book doesn't do a good job of sort of explaining it in the section, and then you get to the homework and there are some weird ones on the homework. So sometimes we'll have something called extra. And these are the ones I think we should sort of look at during lecture before you get to the homework and get frustrated. Throw your book across the room. I mean, that's not good. So what happens if we got both problems at the same time? What happens if you got a fraction and you also have the square root inside the denominator? Kind of stumps students here, but let's see. What can you not have inside the denominator? Can't have a, well, you can't have a 0, right? And then because of the square root, you can't have negative. So technically what you're really looking at is you're looking at when does this be greater than 0. Does that make sense? Can't have the negatives because of the square root. Can't have the 0 because it being the denominator. So really just the inequality symbol changes just a little bit here. But this time you're just not including the 0. Okay, anyways, everybody good there? X is greater than 1. Writing that in interval notation. And there it is. Okay, so dealt with domain. Domain restrictions, fraction, square root, good to go. The homework is going to get just slightly more complicated than what we just covered. Okay. Okay, let me see if this will work here. All right, practice problem number 2. Now we finally get to solving these. We got the domain rules taken care of. And these are going to be a little bit more difficult than you've seen in algebra. All right, so I'll let you guys try yourself here. And again, I'm really just giving you a flavor here for them. This is not at all sort of a whole bunch of practice problems here. We'll deal with a basic one that's usually a tough one in algebra. We'll deal with some special cases, and then we'll go on. All right, and if you get an answer of -3/5, you're doing good. I'm going to start it as well here. So with fractions here, all we got to do to get rid of them, we have to multiply through by a common denominator. Anybody? 6 is good. Yep, let's multiply every single thing here by 6. Technically, we're just doing the multiplication property of equality, right? Multiplying the same thing on both sides. All right, as things cancel here, so I give you the cancellations here just to make sure we got the same thing. And here's what I'm left with. 4 minus 9x is equal to 1 minus 14x. Good there. Got a few people with erasers happening here, so wait just a little bit for you to catch up. Alright, so getting the x's over to one side. Whoa. The constant term to the other, and then divide to get you the final answer. On the homework, you'll see a lot more fractions that you saw in algebra. Just sort of getting used to that. Okay, and the weird cases here. I think most people are done here. All right, let you guys try this one here. More considered something called a nested equation where you got brackets and parentheses inside each other. And also the answer is going to turn out a little bit weird. Alright, so working inside the bracket only, 2 times x, 2 times negative 1. Simplifying that out, should get a 5x minus 2 inside the bracket. Distributing the negative, get you something like this, and then there's trouble. As soon as the variables disappear, the only question is left is it a true or false statement? If it's true, we got all real numbers. If it's false, we got ourselves no solution. Alright, and the symbol for no solution, I think you guys know. Alright, try another one here, another weird one. And again, this one will turn out a little bit weird. And again, if you want to sort of do the lecture beforehand, or at least sort of see where you're at, you can always do the practice problems in the textbook, because that's exactly what we do in class. And so if you want to get a better handle on lecture, I suggest you do that. Then you're sort of just putting concepts together as opposed to dealing with the math behind it. Alright, and how about this? I'll just sort of slowly put down the answers here as we go. So I'm not rushing you last minute here. So we're just checking to make sure you did it correctly. Simplifying both sides gets you something that looks like this. At this point you can even stop, because you notice that both sides are the same. You got a positive 6x and a negative 7 on both sides. If you keep on going, of course, subtract 6x from both sides, and as soon as the x drops out, you're done. This one's a true statement though. So you can say all real numbers, which is absolutely fine. You can also say it as an interval. From negative infinity to positive infinity, anything on the real number line works. And then this one, again, not in the textbook. This you sort of get to see in higher mathematics. There's a symbol for all real numbers that we use. There's a symbol for complex numbers. There's a symbol for integers. And the symbol, it's kind of like an R with an extra little piece in front of it, but that's the symbol for real numbers. That's free. I'm not even going to charge you for it. That's just kind of free knowledge there. Okay, so again, sometimes you get solutions, sometimes no solutions, sometimes all real numbers work. But many times in mathematics, what we really use is we use formulas. So I'm going to do this again to jump to a formula. We either plug in formulas or we solve formulas, whatever we need to do here. And I think this is really the power of mathematics, because if you can realize a pattern, if you can create a formula, what you tend to be able to do is predict the future, which is kind of cool. I think we see it a lot when we look at temperature. As we predict into the future, Why do they have a 3-day forecast? Is because statistically speaking, that is at least somewhat accurate. Once you go to 5 days, not as accurate, of course. 7 to 8, nah. So 3-day tends to be at least somewhat close. Even though I was driving to work, I think like last year, and the weatherman said, no, it's not going to rain today. And as he's saying it, sprinklers, water drops start hitting the front windshield. Like, okay, he doesn't have a window in the office. All right, but let's go for it here. So the directions for number 5 is use the formula to find the temperature in degrees Celsius, assuming the temperature is 50 degrees Fahrenheit. In this case, what's the issue is that we're actually having to use algebra. Because if we plugged in for C, we would be doing pre-algebra. We plug in for F, now we've got to do some work here. So how about subtract 32, multiply by the denominator, divide by our multiplier to C, and we're okay with 10 degrees. Cool. So for word problems, yes, it's customary for formulas to put some kind of unit value on there too at the end. Got a few people still finishing up here. Wait a little bit. Cool. All right, and another one for you. Problem, a little bit of a problem area in algebra. Let you guys try this one. So, perimeter of a rectangle is 2 lengths plus 2 widths, and sometimes, yes, sometimes you got multiple variables at the same time, and so what you really are is you're solving for a single variable based upon other variables. All right, I'm going to try it as well here, at least put up a few things here. So I'm solving for W. I might as well move everything over that doesn't have a W next to it. And then after that, divide anything that's multiplying W. All right, whenever we do this here, what we usually like to do is we like to have our variable on the left-hand side. So in this case, the W is on this side. We switch it over, W on the left equal to the rest of all that. All right, and what the problem is, sometimes in algebra we think that we can divide this 2 right here, and we can't. You can write a different way. Everybody okay with this right here? So P minus 2L divided by 2, or we can write as P divided by 2 minus L. Good there. But you can't just cancel off one of the 2's and call it good. Right? Okay, let's do a couple of word problems here. I'll have to read you the directions here since I don't have it on the slide. And again, let me jump to all these here. So geometry problem, then we'll look at an investment problem. Again, typical ones that will come up. There is a procedure. There's like a 6-step procedure in the textbook on page 82, sort of how to solve word problems. that's something of use? It sometimes is. It kind of gives you a step-by-step process, like identify your variable. What's that going to be? Based upon that, can you put everything else together? Sometimes with geometry problems, it's actually a lot easier to list a diagram, right? In this case. So let's go for it. I'm going to read it here, see if you guys can draw the diagram for it. It says the length of a rectangle is 5 meters more than twice the width. So the length of a rectangle is 5 meters more than twice the width. Find the dimensions of the rectangle, assuming that its perimeter is 28. So if you got it, go for it. If you say, Mr. H, what were you speaking? Let's go for it. So diagram, there it is. If you have a rectangle in your hands, you might as well draw it out. And then it says the length of a rectangle is 5 meters more than twice the width. So that means you'll automatically assume W and L. And because there's information about L, we'll put an equal sign right here. And remember, from algebra, more than and less than. Remember how they work backwards? If you have 5 more than the other guy, you're really adding 5 to whatever the other guy had, right? 5 more than 10 really means 10 plus 5. So 5 more than twice the width. There's that relationship. P is equal to 28. And then we look back to geometry, since this is a geometry problem. We might as well pick a formula from geometry. Okay, so here's our problem. I have 3 different variables. Can't work with 3 different variables. So I want to somehow make it so I only have a single variable here. How do we do that? Plug in whatever we know, right? 28 goes for P. L we know to be 2W plus 5, so that L changes into this. And the question is, now do we have an equation that only has a single variable? Yes. Absolutely. Now we can solve. And again, I'll put up the answer slowly. Kind of look up just to make sure you agree. You keep on going. Alright, cool. Alright, and plugging in for the L, should get 11 for L. Since this is a word problem here, the expectation is, yes, you do write a sentence in English to make sense of your units primarily, and what the variable was in the first place. So how about the width is 3 meters and length is 11 meters. That should be it right there. Debating here. I guess we should do the next 2 here. Okay. Practice problem number 8. Before we get there, let's do a little bit of work here, just real quick, because this comes up in mathematics quite a bit. I'm going to put 3 different columns here. One is amount, the other is other, and the last one is total. Seems like this is sort of the best way to explain it here. Then we'll move on to practice problem number 8, actually. Okay. Again, this should be easy for some. For others, like, oh, okay, got it now. That's kind of what we want. Okay, so let's see. What happens if we have a total of 15,000? I'm going to do it 3 different times, 3 different ways. Let's see if we can get it. We're going to start off something very concrete, work our way down to abstract term. So if you have something that has a total of 15,000, per se, and if we know the amount to be 10,000, what do we know to be of the other amount right away? Yeah, so what we do in our mind, we really subtract, right? We take 15, subtract 10, gives you the 5. Okay, so of course a little bit more complicated. All yours to figure that one out. And really thinking about it abstractly, what are you doing? You're really subtracting from the 15,000. Cool. All right, hopefully you guys did it. I know you're sophisticated Math 15 students, so you got 2,218. I agree. Next question. What happens if the amount is x? What's the other amount if the grand total has to be 15? Go with that. So everybody okay there? You're still subtracting, and this time you're subtracting the unknown amount from the 15,000. Okay, let's try this one then here. This is practice problem number 8. Let me read it to you. Again, if you have your textbook, you can read it as well with me. It's on page 83. It says Tyrick invests $15,000, some in stocks and the rest in bonds. So if he invests 3 times as much in stocks as he does in bonds, how much does he invest in each? I'm kind of blending practice problem and example problem together. Okay, so here's what we got. We got him investing some in stocks, the rest in bonds, and we want to go to an equation because that's what we really want here, and see if this makes sense to you here. If x is one amount, and he invests 3 times as much in stocks as he does in bonds, that means the rest has to be the 15,000 minus x. We're good? And again, let you guys try to finish it off. I will put the answers as we go. But just the whole concept of, if you know the total, you don't have to set up 2 different variables. You can just subtract from the total to get the other variable. All right, so we do that, adding up, dividing by 4, and hopefully you guys got this. And the question is, how much did he invest in each? So I'll let you figure that one out. All right, so here's what I got. See if this makes sense here. So Tyrick invested 11,250 in stocks and 3,750 in bonds. Are we good there? With an extra I within. There you go. Okay, let's look at the 2 formulas you may run into in mathematics here. First one is this one here. Simple interest. Used quite a bit. If you own a credit card, that's the formula that tells you how much you owe extra. how much you're paying them to use that money. If you have a mortgage, same thing, end of the month, what they do is they figure out your daily rate for the mortgage times your average rate for the month times the number of days in the month. That's it. And there's your interest. What really gets interesting is when you move into compound interest. And then Albert Einstein said that compound interest should be the eighth wonder of the world. Just the way it works. It's interesting. So we'll see. We'll see how that works. Okay, there's that one formula. Let me jump to a different formula, then we'll go back. The other formula, which you should be familiar with, this one right here, called the DIRT formula, right? Distance is equal to rate times time. Okay, don't have time to do both of these formulas here, so let's do one of them. And how do we set it up? Example number 10, then textbooks tells you sort of how to set up the DIRT formula. So in the textbook, let me come back to it here. Practice problem number 9 and example number 9, they're actually totally different from one another. So let's do it this way here. All right, let me read it. You guys can read with me if you like. So 1/5 of my capital is invested at 5%, 1/6 of my capital at 8%, and the rest at 10% per year. If the annual interest in my capital is $130, what is my capital? And so example number 9 actually was very similar to example number 8, but practice problem number 9 more similar to the DIRT problems here. So let's handle this here. So first things first, if you make up this little grid here, notice that there's 3 investments. One at 5%, the other one at 8%, and the other one at 10%. So that tells you how many rows you have. And then the DIRT formula, or the PRT formula, goes across here. And then as long as you can fill in the grid, you're fine. So let's see. It says 1/5 of the amount was my first investment, 1/6, and then we got the rest over here. How do we do that? Well, let's see. If I take X to be just the investment part, isn't that 1/5 of X? X is my total investment. Is that 1/6 times X would be the rest of it, or the 1/6 investment? And you guys get to tell me what the rest would be. It won't be X. X is the total investment. You guys work with fractions here, huh? She whiz. I'll go with that, yeah. How about we add this up and then we subtract it from 1, is that right? Because the grand total would be 1. So first of all, I got to add it up here. So 1/5 plus 1/6, common denominators. How about 11/30ths? Will that work? All right, and then subtracting that from 1, so that would be 30/30ths, or how about 19/30ths? We good there? Again, that whole concept of total again. So the rest would be 19/30ths X. The rate is always a decimal. So it says 1/5 of my capital is invested at 5%, coming in as a decimal. Everybody okay with 0.05? 1/6 of my capital invested at 8%, so how about a 0.08? And the rest at 10%, so how about a 0.1 or 0.10? Again, long problem here, but I at least wanted you guys to see it. T, got to put that in. The only thing is it says this is annual interest, so we're just looking at a single year. Cool, so everything's ones. All right, you guys get the fun part here, because notice the formula, just like the DIRT problem, it's rate times time equals distance. Here it's principal times rate times time equals interest. So what we got to do is we got to multiply this all out over here to get our I value. And I like grids, especially for word problems here, because once you fill in the grid, you know exactly what column you're in. This works especially good with interest, with distance, and with mixture problems. If you can set up a grid, those three always work inside a grid. Cool. All right, so let you guys do the first one here. I'll show you the answers here for the cycle. So multiply 1/5 x times 0.05 times 1 and see what you get for I. See what should be at the end there. Those of you that say, Mr. H, what are you doing? Here we go. Okay, what's the easy way to do this? Well, I got fractions and decimals at the same time. I can convert one or the other. How about I just convert the 0.05 into a fraction? Isn't that really the same thing as 5/100ths? Right? Isn't this 8/100ths? This is 1/10. So let's see if that makes sense. I converted the 5 into 5 over 0.05 into 5 over 100. Those cancel, leave me just with, that's fine, I can have a fraction here. 8 over 100, reducing, gives me 1/75. And again, 1/10. Again, like this word problem, lots of fractions in it, lots of concepts of decimals, and a lot of good stuff in here. Okay, multiplying out, don't forget the x, because there's an x in here somewhere, right? So see if this makes sense here. We got 1 over 100x now, 1 over 75x, and then we got 19 over 300x. Okay, and all that has to give you a grand total? Something or other. I think it's 130 according to the practice problem here. So notice what we got, we just have the interest itself. So now usually on dirt problems here, you're either adding this stuff or you're setting equal to each other. You'll see that a little bit later. In this case, interest, you're going to add it up to the total for the interest. So how about this? Took a long time to get to our equation. Not to scare you, this is the longest one in this section. All right, I'm going to speed it up because I don't want you guys to get lost in the math behind it here. Looking at this here, you guys tell me, what is the greatest common factor or greatest common denominator? Yeah, 300. Let's multiply everything by 300. That'll work. And I like this. Once you do that, everything nicely cancels. You should be left with this right here. And again, just don't want you to be caught up in the math behind it here. All right, adding it up, let's see, that's going to be 7 plus 19 or 26. Divide by 26, and we get an answer of nicely 1,500. And again, writing it to finish off the problem here, at this point probably would be this right here, right? So I had $1,500 to start with. I got $130 worth of interest out there. As far as investments go, I'd like to tell the story here. Hopefully I didn't tell it in the last chapter. Did I tell you guys about working for Bank of America or no? No? Okay. When I was in college, I used to be teleservices representative, which is I was on the phone for Bank of America. And at that time, being a college student, not knowing what life's about, still haven't quite figured it out yet, but closer. These people are calling, and I'm thinking, why are these people calling always asking for interest rates on something called CDs, or certificate of deposit? That's when you take your savings or something, you lock it in for a certain amount of time. 6 months, 10 years, whatever you like. So these people were calling, and I mean, I just started. So the going interest rate for a CD was anywhere from 8 to 10, sometimes even 11%. And some, as people were calling, they were locking in their money for 10, 20, 30 years. Like, why is that happening? Like, there may be something here. So, anybody know the interest rate on a CD right now? It's about 0.75%. And so the people that locked in their CD for 20 years at, I think the highest it went at Bank of America was, I still remember, I don't know why, 10.31%. So getting 10% on your money for the next 30 years, not bad. So, okay, with that, let's jump to, I'm going to skip practice problem number 10. It deals with the dirt problem here, but it's okay. Deal with the distance problem. I think you guys, the other one's pretty good here. Sometimes, practice problem number 11, sometimes you are able to go directly to an equation. Sometimes it's given, you just need to plug in the values, whichever values you need. So in this one, I'll read it to you here. In fact, it says in the introduction, there's a bungee cord with 140 to 150% elongation, which means it stretches that much. So if it's 100 feet, it can stretch up to 150 feet, depending on the weight of the person jumping. So used in contest bungee jumping from a bridge of 120 feet above the water. The show's producer wants to make sure the jumper does not get closer than 10 feet to the water. So how long can the bungee cord be that no contest is 7 feet tall? So you figured no one's going to be over 7 feet tall. And so we're going to change it here. So what length of cord should be used in example 11 if the elongation is 200 feet instead of 140 or 150? So our rope is a little more stretchy. Our rope can actually double. So depending on the size of the person, 150 feet of rope stretches to 300 feet at the most. And so what we have is we can go directly to an equation here as long as we got it here. So extension of the cord. Why is it 3x instead of 2x? Let's see. Because the length of the rope already, right? If you can stretch it out twice that amount, so the full stretch of it will actually be 3 times that amount. We're good? Maybe, sometimes. So elongation just means how much of the stretch is occurring, as opposed to how much does it go. Okay, so we said 10 feet. Oh, sorry, 7 feet is the body length of the person, no more than that at least. And then you got a 10 feet buffer to the water just in case. And again, what is example 11 saying is that you can somehow sometimes go directly to equation if you have it. Just like you do for the temperature. Alright, anyways, solving this one just real quickly here. Subtracting from 120, dividing by 3 gets you to about that much. So if you ever look at bungee jumping here, you don't go the full length of the rope, right? There's always a cutoff point to the rope, and of course they're measuring it to make sure you don't hit yourself. At least not too bad. Okay, we good? And then, sometimes it just kind of does weird stuff here. So that person did not measure correctly, so like, oops. So you got a little wet. And at the same time hitting the water that speed, yes, you could faint. Yes, you could do some damage in your neck. Yeah, you're not supposed to hit water. That's not a good thing. All right. I'm going to try to get through 2 more sections we're going to go a little bit faster, a little bit less work here. So we move on. We're graduating from linear equations, because notice all those were just linear equations. So let's quickly review how about all the quadratic equation stuff we got to deal with. And we're going to quickly review, first of all, factoring, which we already reviewed, but factoring inside an equation. How about the square root method? I think you guys have seen that before. And how about the completing the square? Remember that from somewhere a long time ago? And then eventually, sometimes when you can't do anything else without factoring, then we use the quadratic formula. Okay, so what is the quadratic equation? There it is. It's whenever you have something, well, exponent of 2 on the x variable. You missed the video, the bungee jump video. Oh, that's so. Yeah, see? Came too late. All right, in the quadratic formula, what's so important of it is we can actually make the quadratic formula become a linear equation. How in the world do we do that? We do it by factoring, right? Because when you factor down, don't you get like x plus 4 times x plus 3? What you in fact did is you've made a quadratic equation into a linear equation. That's exactly what you want. And the other one, hopefully you guys remember something called the zero product property. Remember that one? If you have two things multiplying to give you 0, you can split them off to say one of them has to equal the 0. I think you guys are familiar with that. And again, just quick, a lot of good reviews here with this chapter here. So I'll let you guys just try it. The hint is, I think, set it equal to 0 first. Is that right? Alright, I'll give you guys a little bit of a head start. Again, just because time-wise, I want to get through a few of things here. So I'll just start posting up the answer. Just kind of look up from time to time to see if you are okay with what I'm having on the board. Factoring that down, again, bigger numbers than you've probably seen in algebra. Still think through it here. Two numbers, multiply 84, add to 25. Put it up here just in case. Here it is. Everybody agreed. Let's see what the 21 and the 4, is that right? And the zero product property says I can split that off into two different pieces. There it is. And now I've made myself two linear equations to solve. And that's cool because I know how to solve linear equations. There it is, and done. So again, the way the book is going to put it is in these braces, and that's okay too. Let's see, it doesn't necessarily have to be in that order, because whenever you put braces, you're talking about a set, and set has no order. So in that case, you could have put the -4 first, then the -21. You'll notice though, almost always the book is going to put the lower number first, and then sort of go higher and higher. But that's okay. All right, another one here, just to try. All yours. And again, hopefully still setting equal to 0. And this one's kind of a little bit different here. If you factor out the m, that's all you need to do. As you take out the GCF, finish there. Now you can split them off because you still have, now you have all linear equations, or you can think about it as factors here. So m is equal to 0, or add 5 divided by 2. That good enough to give us the final answer? And again, in set notation, there it is. Alright, good. I'm going to skip practice problem number 3, and I'm going to jump to the square root property. And again, I think you'll sort of see this a little better, or remember a little better once you see it in action. Alright, it says this: if you have a perfect square equal to some kind of number, what we can do is we can just take a square root of both sides, put a little plus and minus. So whenever you are the one taking the square root of both sides, you got to put that plus and minus in there. And again, the only thing is, unless it is a word problem and you know that something has to be positive, like a distance or something like that, that's the only time that we say you don't need to include that in there. Okay, but let's hit on practice problem number 4. There it is. We got x plus 2 squared. Alright, and again, I'm going to try it here already. All we do is we put square root of both sides. Alright, and again, mathematicians are lazy because you should actually put a plus or minus over here. The reason why they don't is because the square root and the 2 are going to cancel off anyways, right? So why make extra work for yourself when you don't have to? It's going to cancel off anyways, so x plus 2 is equal to the plus or minus square root of 5. Finishing it off, solving for x, how about we just subtract 2? Alright, we're good there. Customary in mathematics is to write the integer first, and then any square roots or any complex numbers go after that. So, okay, again, just give you a flavor, remind you from algebra, like, oh, I remember that. That's cool. Okay, the next one is something called completing the square. And so let's go with this one here. This one's more of a process. Doesn't really have a formula next to it. But if you think back, you got to think back to perfect square trinomials. So let's go for it. How does this process work? And again, if you got it, go for it. How do we solve a quadratic equation by completing the square? Well, first, what we do is we move that constant term over to the other side and leave a little bit of space here, because we're going to fill that in with whatever forms that perfect square trinomial. Alright, how do we do this here? Like, it's almost like this. What number, if you square it, would form this number here? If you were to double it, would form this number here, right? Okay, easy way to do it. How about this? We take the middle term, divide by 2, and we square it. Do you guys remember that as the perfect square trinomial? And I think we know this here. Whatever do to one side of an equation, we better do to the other here. So how about a 9 on that side as well? All right, you can think back to the trinomial, how this factors, or even better yet, you can think of the number right before you squared it.
Why did you divide it by 2?
Why did I divide by 2? Let's go for it. And again, ask me the questions if you need to. Let's take a little journey. Uh-huh. Let's take a little journey here. X plus, let's go 3 squared. That should be a 3 there. Remember, what happens here is we're going to FOIL this out. You get a x squared. You get a 3x. You get another 3x. And at the point, you get a 9 here, right? So notice what happens, this guy doubles. Or you can think about it as being 2 times 3 times x. Well, for us, the process is now in reverse. We need to think about, okay, what's doubling to get you that? And so we just go in the exact reverse order. We think if we divide the 6 by 2, and then again if we square it, it would give us what we need here. Cool. So it's the backward process. Or you can think of it as the formula. Remember this little formula? A plus b squared is equal to a squared. And then what did we do here? We did 2ab. And so we know this is already the x, so that's no problem there. We forget about that. But we take this 2, and essentially what we're really doing is we're taking the 2b, dividing it by 2 to give us that little b right here. We square it and it gives us that right there. Cool. Just to complete the exercise here, a minus b, you know this is a squared minus 2ab plus b squared. And again, because the minus being there, still divide by 2, because what we want is, we know that b value is just going to be a negative, that's all. When we square it, it still gives us the b squared. Cool. Alright, tell me if you guys agree. This should be x minus 3. The other side should be a wonderful 2. Hey, doesn't that look like practice problem number 4 now? I think so. Rhetorical question. Take the square root of both sides, plus or minus. Cancels on the left. Left with a plus or minus root 2 on the other side. Add 3 and voila, we have solved the problem. Okay, when is this really used? Used when we have to deal with circles, which we will in chapter 2. We do have to complete the square because we're actually trying to form perfect square trinomials. The other time it's used whenever we're graphing parabolas, and we'll talk about it whenever we want to switch forms. And we use perfect square trinomials to get to what we want to see out of that. So we'll see it later on. Chapter 2, chapter 3. We'll see it there. Okay, so that's completing the square. I'll let you guys try one here. A little bit more difficult one. So can you solve this by completing the square? Okay, and if you got it, like Mr. H, I remember this. Go for it. If you're not quite sure, stick with me as we go through it. It's that little 4 out in front that's the problem. Alright, those are ahead of me, keep on going. Those who want to work this out with me, let's go for it together. So first things first, what we have to do is we have to get that 25 to the other side. So everything else remains the same, but that 25 is gone. Okay, here's the little tricky step. And if you started dividing the negative 24, you did wrong. Ready? Because you have to factor out the 4 first. In order to do this process, the x squared has to be by itself. Alright, I got 4 erasers going. Got 4 of you guys. Okay, so we take this negative 6 and we divide that guy by 2. Gives us, hey, negative 3 again. Okay, that's no fun. Adding 9 here. Yes, what should we add to the other side?
The other side. What? Negative.
If you said 9, it's incorrect. What do we add to the other side? Waiting for a correct answer. I could be here all night, no problem. 36. Okay, yes. How come? Yeah, you got this little multiplier still, right? So careful here, yep. Technically what you're really adding to the left is a 36, therefore to compensate a 36 to this side. Alright, 4 on the outside still. Gotta, let's see that would make an 11. Alright, yes, we've got to get rid of that 4 in front, so let's divide both sides by 4. So let me rewrite it real quickly here. That, divide by 4, divide by 4. I give myself x minus 2 squared over equal to 11 over 4. And you guys get to finish it off with a fraction this time. Those fun fractions. All right, square root both sides, plus or minus, again. There it is, x minus 3 now by itself. And this one got a bit of work here to do. Hopefully you guys remember this. You can split this off into 2 different pieces, and then you got the square root of 4, which is really just going to be 2 anyways. Once you simplify that, and then we can add 3 to both sides, and how about final answer is 3 plus or minus root 11 over 2. Good there? Alright, completing the square. This is kind of fun. Good review of quadratic equations here. So factoring if we can. Square root method, the completing the square method, and then we have something like when all else fails method. Quadratic formula. Can't factor it. Not really appropriate to do completing the square. Can't do the square root method. Got yourself the quadratic formula method. You want to use an analogy, you know, like this is the sort of the Hail Mary pass. Like, okay, factoring doesn't work, nothing works. I'm going to try quadratic formula. Could have helped the Seahawks. I don't know, probably not. Okay, so all yours here. Oh, it's not going to factor. Don't even try. But all yours to finish this off using the quadratic formula. And again, I'll start putting down the answers here slowly. Look up a few just to agree, or you just want to make sure you're on the right track. It pays to know the quadratic formula, just want to say. Has worked out in my life. I was at Blockbuster, which already dates me. But the general manager that was there, she was taking a math class. And so she's sitting there, and she's doing an algebra problem, and she's trying to solve it. And she's like, what's that darn formula? The formula that I can just do that and I can get the answer? So I'm in line, trying to rent a movie, and I was like, it's called the quadratic formula. it's negative b plus or minus square root of b squared minus 4ac over 2a. It's like, really? Seriously? Yeah, just do it. She goes, yes, awesome. It goes, movie free. You want another one too? Like, yeah, I'll take 2. So, it pays. And again, tell me if you agree. All right, this one works out to be a perfect square, not necessarily going to be so, and I actually lied to you. This actually you could have factored. Sorry about that. Plus or minus 7 over 12. I don't know if I lied to you, no, because lying means I was trying to deceive you, so I misled you, I guess. So multiplying that out, and again with fractions, make sure you put it in simple form. And how about a 2/3 and a -1/2? We good? Okay, with that, that is for quadratic equations. That's it. That's the way we solve quadratic equations here. So we're going to do one more section here. Still dealing with equations, but we've got to talk about the complex numbers. And really we're trying to get to the point of solving them. All right, so by definition here, hope you guys remember this here. Definition of I, which is the imaginary number, or the complex number. There's a subtle difference there. But by definition, I equals the square root of -1. Where does this come out? In about 500 years ago, a medical doctor, sort of his hobby was doing mathematics, abstract mathematics. That's already weird by itself, right? Hobby of doing math. But in sort of the known academia of the world, what they would do is whenever you got a negative inside the square root, they would just cross it out, like you know how we do with word problems. When there you got a negative distance, you're like, that can't happen, just cross it out. Well, the medical doctor, he wasn't really formally trained in mathematics, so what he did is he actually just left it. He actually put in a letter for it, like I or something. And lo and behold, kind of fun, 300 years later, when we have electricity, we figure out, wow, I is actually the background mathematics for electricity, or the way we think about electrical engineering. So kind of fun to sort of see that, like, wow, it actually is useful. Because he got a lot of ridicule for actually doing that. Or like, you should just cross it out. What are you doing? But Dr. Cardano did it, and that's kind of fun. We had the mathematics in place for electricity. All right.
Did you take a math history class?
Yeah, part of my major is a math history class, which was fun. All right, so if I is equal to the square root of -1, if we were to square both sides, what we get, tell me if you guys agree, I squared is -1. Why do we use this? Because we're going to simplify stuff. Whenever you see I squared, we're going to just change it to -1 because it's the simpler form. Cool. All right, let's go for it here then. So this is called the imaginary unit. This is the one that has the I next to it. A complex number is made like this. You have z. Z is considered a complex number. You got a plus bi. So if you see an I part over here, you know you got yourself a complex number. This is the real part. This is the imaginary part. Let's see if this will work. All right. Kind of fun though, if you think about it. In life, let's say we write the number 3, right? You guys been doing that ever since first grade or so, right? Writing, 5th, some people, a little slower. But if you just write down 3, What we don't really see in here is, isn't that really just 3? Right? And then after that, isn't there actually like this? Right? There's variables, but they're all power 0, which technically just makes a 1. So now we know that this is really a plus 0i. So by writing down a little 3 in first grade, there's all that stuff afterwards. And then there's more stuff than that. And this is called ordinal numbers here. Then it's kind of fun. There's a lot of complexity. And the question is there infinite complexity in numbers? Yeah, that's a fun question. We're not going to answer that question today. We'll just keep on going. Okay. Da-da-da-da. All right, I think we're ready to move on to this one right here. So practice problem number 1, just real quickly here, because some of the homework questions are like it too. Practice problem number 1 says, identify the real and the imaginary parts of each of the complex numbers here. So for A, the real part is the -1. The imaginary part is the 2. Notice for the imaginary part, it's not the one with this I is not included in it. It's just the coefficient of I. All right. A little mess up here. This should not be an equal sign. This should be a minus sign right here. So it should be -1/3 minus 6i, not a negative there. Cool. All right. So real part is the -1/3. Imaginary part is just the 6 or the -6, because you got to include the sign of it here. So again, ever wrote down an 8, you were really actually writing down a complex number, with the imaginary part being equal to 0. So let me write it in right now. All right, imaginary part is equal to 0. All right, let's go for it here so we can finish this section here. So how do you know whether two complex numbers are equal to each other? Well, first of all, the real part have to be equal to each other, so A is equal to C. And then also the B and the D have to be equal to each other. All right, sort of a more, again, this is sort of going a little bit into electrical engineering here. The RE means the real part, the IM means the imaginary part. So sometimes what we do is we say Z is the complex number, W is the complex number. So the real part of Z should equal the real part of W. The imaginary part of Z should equal the imaginary part of W. But again, this is sort of going a little bit more abstract here. Okay, so let's go for it here. So you guys tell me, or prove to me, that these two complex numbers are equal to each other. Or what does A have to be? And what does B have to be for these two to be equal to each other? Alright, again, just like the previous slide, sort of connecting ideas here. Doesn't that mean that the real part has to equal? So doesn't that mean that these two have to equal to each other? So 1 minus 2a has to equal to 5. For that to be true, and if we solve for that, let's see, that would be 4 now, divided by -2 gives us -2. So a would have to be equal to -2. If these two are equal to each other, the imaginary parts would have to be equal to each other. So the only thing is, since it's subtraction, technically there's a little negative there. So how about 3 equals to a negative 2b minus 5? And again, a little bit more abstract than we did in algebra.
Why do you subtract?
Because there's subtraction in the problem itself.
Oh, not plus? Oh,
So I made it into a negative
oh.
to take it out of there. Alright, distributing the negative, subtracting 5, divided by -2, leaves us with b equals 1. So there it is. A would have to be -2, b would have to be equal 1 if these two guys are equal to each other. Okay, that was a little bit of a sort of abstract sort of notion of them. But we are going to review the algebra stuff. So add, subtract, multiply, divide, all the good stuff that you should have seen in Math 63. Let's go for it quickly here. So let me give you the formulas for it first. If you're sort of formula minded a little bit here. So how do we add these guys up? Well, all we do is we add the real part to them, and then we add the imaginary part. How do we subtract? We subtract the real parts, and then we subtract the imaginary parts, and we got them. So, okay, another little goof up here. This should be 1 minus 4i, not equal to. So 1 minus 4i. Ha, better. Alright, so hopefully we can add 1 and 3 make 4, and a -4 and a 2 make a -2, now with the I next to it. So adding reals, adding imaginary parts. Of course, it gets a little more complicated. All yours for this one, subtract. Alright, again, what I probably would do, I'd just change it to addition. I could think about it a little easier, but if not, you guys can think about it here. 4 subtract 5 makes a -1. 3 subtract a -1 makes a 4i. And of course, we have to include square roots in here. That would not be fun if we didn't. Alright, and the slightly weird one here. Alright, and yes, what you had to do is you had to figure out what in the world would square root of -3 be. Everybody okay with the 3i there? And then an 8i. Everybody good there? Okay, going on with that one here, let's move on to multiplication. And again, if you need the formula, that's fine. But I think generally what we do is we just use FOIL, because FOIL works exactly the same way. So again, there's the formula if you need to. Not that useful, because it's a lot easier to sort of think about it as binomials here. Cool. All right, let's go for it then. So practice problem number 4. And again, if you do want to read ahead and if you want to try to practice problems before lecture, I totally encourage it, because you guys will sort of at least have things thought of in your mind already here, and then you're putting sort of pieces together. That's a really good thing. All right, and again, I'm just going to keep on going here. So FOIL method, that's exactly what we use here. 2 times 1, 2 times 4i. Negative 6i times 1 gives you negative 6i, and the fun part here. Negative 6i times 4i makes a negative 24i squared. Then of course the alarm goes off in your head, right? Ding, ding, ding. I squared we know is negative 1. So let me rewrite it, putting a negative 1 there. Again, do you have to rewrite it like me? No. What you probably should do, you probably should go like this on the first step, right? You know negative 6 times 4 is a negative 24. You know you're going to have an I squared there, so how about just put a positive 24, just change the sign. But yeah, we do have like terms to put together here. So 2 and 24, 26. 8i subtract 6i makes a 2i. Good there. Okay, easier one for you guys. All yours. Should be done by now, but let me just kind of put in the steps here just to make sure we're good. Cool. All right, and noticed what I did is I had to move the negative 15 out to the front. Again, by definition, a complex number is the real part in front and the imaginary part in the back. Okay, and this warning comes through here because this is probably a mistake that algebra students make quite a bit here. Do you guys remember from algebra, when you have a square root of a times the square root of b, we can multiply these guys together? Okay, that only works if they are positive real numbers. Doesn't work any other time. So if you have something like this, negative square root of negative 9 times the square root of negative 9, what you should happen is you should change this to a complex number first, multiply it, and then simplify. Notice you get a negative 9. If you did it this way here, so square root of negative 9, square root of that makes 81, and then that's wrong because then the sign is off. So we got this little deal here. True. Square root of a negative number times itself is not the same thing as the product of those then taking the square root. Okay, just to be mindful of that. Let's try just practice problem 5a. And again, the whole concept here, if you can change it to a complex number, do so, and then start doing the simplification. Again, I'm going to start as well here, so change that up into a complex number first before I do anything else, or else your signs will be messed up later on. And this one actually does not really have a special form. You just simply change it up to two different pieces here. There's a pattern, but we don't consider it a special form. And then, of course, we use FOIL again here. So 9 minus 6i. And let's see what we got at the end here. We got a 2 times 2, which makes a 4. But because we're going to have the I squared, how about a minus 4 right away? Alright, and simplifying, hopefully we're okay with this one. Okay, we actually have to do 5b because it's a lot more complicated there. So I'll let you deal. How about this one here? Alright, again simplifying to a complex number. When you do that, we still got some trouble because we still have square root of 2. So I was able to take out an I in front, but I still got square root of 2 for the negative 8. Again, it was a negative 4 being the perfect square. Take out a 2i, but then still left with the square root of 2. So let's go for it here. So how about 20? 5 times all of that. Remember, if it's outside number, the 5 and the 2 multiply together, and everything else stays the same. How about a 10i square root of 2? As you multiply the inside terms here, technically there's like a little 1 here, right? So it's like 1 times 4, or 4i square root of 2. Alright, and the fun one. Let's see if we can get this guy all together here. As I multiply this guy, I'm going to get a, let's see, 1 times 2, which is 2. Square root of 2 times square root of 2, which is 2, and 2 times 2 is 4. Is that right? But I'm also going to get I squared, so how about a, I'll do it off to the side just real quickly here. Everybody agreed there, and there, and there with a minus 4? If you did that on your head, good. Of course I did that in my head. You doubt me? Okay, finishing it off here. Notice the square root of 2's are similar, or like terms. That's good, because then we can put all those together here. How about a 14i root 2? It's customary to put the I in front of the square root. Some math books do put it at the end. You have to be very careful with the square root. You always want to end it wherever the number ends. So the square root bar has to end there. Fun one. Okay, so again, sometimes it will look like this. Sometimes you can actually write it like this, and that does mean the same thing. Since it's the square root, it's kind of like, well, which one do you write first? They're both square roots. Okay, there is a special form. There's 15 minutes left here. It's called the conjugate. You guys remember the conjugate? Whenever you deal with complex numbers, there's actually even a notation for it. A conjugate actually has just a bar line over the complex number. So a plus bi, this guy means the conjugate, and remember the conjugate is just the opposite of your imaginary part. Cool? With the sign in the middle being changed. Got a few more things to do here, so let's go a little faster here. Practice problem number 6, it just says multiply by the conjugate. See what you guys get. Alright, so x plus 6i, so the conjugate would be 1 plus 6i is going to be conjugate 1 minus 6i. Multiply the first terms together. Everybody okay with 1? Multiply the outside terms, negative 6i. The inside terms will give you plus 6i. And then the last term, let's see how to do this here. 6 times a negative 6. Negative 36 with an I squared, which means a positive 36. Okay, i's cancel. You know what? If we're going to do that, why even multiply the outside terms and the inside terms? Is that right? Faster way? We forget the inside terms and the outside terms. Whenever you multiply the conjugate, all you do is multiply the first terms, last terms, and done. We good? Why work more than you have to? Okay, and then the unusual one a little bit here. What happens if you're trying to, at least what is the conjugate of this one? Yeah, technically, let's see, that's the complex, that's the imaginary part, right? So, technically, isn't it this right here, right? There's a 0 there. As the real part here, so the conjugate of negative 2i would just be a positive 2i. Multiplying that together. I squared, and how about we get ourselves a wonderful 4, and that's it. Alright, why do we need conjugates? We need it for this problem particularly right here, right? Whenever we divide complex numbers or we simplify quotients of complex numbers. So somehow we have to get rid of the I in the denominator. We just figured out from the last 2 problems here. The way you get rid of it is you multiply by the conjugate, which is 1 plus I and a 1 plus I on top. Alright, and what I like to do sometimes here, I like to leave the 2 on top still by itself without canceling, and you'll see why, but let's go with it. Let's just start here. So conjugate on the bottom here, 1 times 1 is 1. Negative I times a positive I. Positive 1, right? And on top I would distribute the 2, 2 times 1, 2 times I. Simplifying further, hey, look at that. So notice that bottom, sometimes the bottom or the denominator will cancel with the original numerator. But I think you guys are sophisticated math. 15 students, you guys can do that, right? 1 plus I. Alright, let's go for it here. Of course, the tough one. Can you guys do this one? Alright, I just want to make sure we finish here on time here. So first of all, change that to a complex number. Everybody okay with the 5i? Multiply by the conjugate. And again, if you're ahead of me, that's perfect. Alright, and then the conjugate will give me 16, looks like, plus 25 on the bottom. On top, I got a distributive property here, negative 12i. And how about a positive 15 I squared, which makes a minus 15. Alright, simplifying that further. And notice what I'm going to do, I'll move the 15 out to the front. Alright, and again, it's customary with complex numbers is that they're never ever one single number. They're actually two components. There's the real part, imaginary part. They're two separate numbers here. So it's customary mathematics, whenever you have a denominator, always to split that denominator. Two different pieces, because you want the real part and you want the complex part separate from each other. Okay, because of time, we're going to skip the wonderful electrical engineering application. That's no fun. But we are going to go to right over here. And we're going to solve this one. You could actually solve it by the square root method, but I'm going to suggest you guys solve it by the quadratic formula. So let's do this one together, and then you guys can have the other one here. It's 4x squared plus 9 is equal to 0. Good. That's already said equal to 0. A is 4. B is 0. We're good. C is 9. So I can put the quadratic formula. Minus 4 times A times C all over 2 times A. And remember, again, we're dealing with the complex numbers. Well, let's see if we're doing 416. 16 times 9 is 144, so negative plus or minus negative 144 over 8. How about a plus or minus 12i over 8? Okay, what you should know, and again we'll reiterate it again, whenever you have a complex number, you know automatically you don't have anything crossing the x-axis, right? Because you're never hitting the real number line. But reducing, everybody okay with this one? Negative plus or minus 3 over 2i. One, two more problems here. I think we can finish, or 3 more problems here. We can finish up with. Okay, let you guys try one by yourself. Go for it. Gotcha. Okay. In Fireball, just real quick here. Let me give you the answer, just to make sure we got it. Set equal to 0. Quadratic formula. Simplifying as much as we can. Negative 36, square root of negative 36 gives you 6i. Whoa. And eventually splitting the 2 to both those pieces and reducing gives you 2 plus or minus 3i. Whether or not you have real answers or not, and it's all based upon this right here, right? Which we just saw. If this is negative, you only have complex numbers. If it's exactly 0, you do have a real solution, but you only have one real solution only. And if it is greater than 0, you have yourself 2 real solutions. That's kind of what we look at when we're going to be doing this, and we're going to be graphing parabolas. when we get to this step, can be crucial. We'll take a look at the sign on it. If it's negative, good. That means we know we don't have any x-intercepts. And if it's positive, we got to find the x-intercepts. All right, so this is the chart you guys should be familiar with. Again, this probably should go in a 3x5 card sometime if you have not memorized it yet. So there it is, 2 real solutions if it's positive, 1 real solution if it's negative, and no real solutions. They are going to be conjugates of each other, but no real solutions are going to be 2 complex solutions. Let's see. There's the bell, so I give you one more problem here. So the directions for 10 is use the discriminant to determine the number and type of solutions, and that's it. So don't solve it, just give me what type you have. Alright, so here's the discriminant. Just plug it into that right there. Again, not even the quadratic formula. Don't need it. Just that little formula there. 36 subtract 36 gives you a 0. So what do we know? Cool. We got ourselves 1 real solution only. And as we start graphing in chapter 3, we'll find out, hey, that means that there is a vertex right on the x-intercept. That means we have a minimum or a maximum right on the x-intercept. All the good stuff we're going to get to learn. Cool. I'll stop with that one because I'm sure you guys can realize how to do the other ones in light of this.